So the V0 is a barrier you want to cross. Barrier you want to cross. But E itself is how much energy given to the particle. There are two different things, you understand. One is how big a barrier you have. The other one, how quickly you want to push these guys go through it. How large the energy is sent into them. And this is supplied by the battery itself. So the battery, so there are two different things. One is go from here to there, how large energy you send into it. So these are two different things. Good job. So this is a huge difference. One is, again, let me summarize it. The quantum world case is a localized state, but the tunneling is delocalized state. So that's why we do not normalize the wave function in this sense, because that's proportionality is related to that. Sounds very good. I'm very satisfied with this answer. Let me move on. Next question.
Okay.
Yes.
So just to go with the energy, like, so V0 is the energy barrier that it's trying to get across. Well, within like circuits, what application does that have?
Oh, that's
because like, is it a capacitor?
Oh, this is enormous applications. Let me just use that as an example. Let me just use the qubits as example to make things a little simpler. The qubits, you saw that the figure. Qubits case, we have aluminum oxide, aluminum, like this. So for instance, if I want to make the barriers bigger, larger, I want to make this guy thicker. So insulating layer is thicker. And so this way, it will change the resonance frequencies of the system. We normally use a microwave. You guys did microwave experiment. We use just a microwave. Send the microwave in, and then the qubits is going to absorb that amount of energy. If you make this guy as thinner, and then versus thicker, you have two different characteristics involved when you send these signals into it. Commonly, we make them thinner because if they're too thick, the terminal effect will be small. So usually you have down to maybe a few nanometer, which we have experiment of the data in the book show you how big thickness that was. And this particular feature was, and we also have some other examples, which is chapter 9. Chapter 9 is called atomic force STM graph. If you are really eager to know that, I can tell you immediately. Just give me a second. This was one of the things that I really insisted. We need to discuss this. I share this is on page figure 9.12. 9.12. This is on page 280. Page 280. Page 280. Figure 9.12. 280. Page 280. Did you see the figures? The left is on the conductance in the carbon nanotube, and on the left, conductance changed when the tube. And what it did was the tube dipped into the mercury. You pull out the, here's a part of mercury. You move this the nanotube gradually move away. You remember mercury is a liquid, and then when they did it, you see there's a huge jump of this ones. And that's a quantization process going on in this case. And you notice that delta Z equals plus minus 2.5 micrometer, which means you shift this guys above. This is the one where you can change the barriers, like what I was saying. Right-hand side even better. Right-hand side, what they did was, it's just so funny. And this is from oscilloscope, by the way, oscilloscope. What they did was just two copper wires, and they want to attach a remote, attach a remote. When they do it like this, just do it like this. Just do it like this. And then when they look at the IV curve and take a derivative of IV curve, they found this conductance is quantized jump. This is one of the most beautiful experiments. So I run out of time, but if you guys are interested in this would be very interesting. Just so you put two wires, touch each other, connect to the oscilloscope and check the river oscilloscope, you get these quantization features. Yeah. Anyway, I cannot do like this forever. I mean, I just let me finish this. I stop you. Ask question. Where is my next one? Okay. So why we did not normalize the wave function? Why we did not normalize the wave function? Tell me. Why we did not normalize the wave function?
Oh, because it's not localized.
Exactly. This is a rhetorical question. Okay. Cody, what is the wave function in region 1 look like? Yeah, look at the notes. What does the wave function look like in region number 1? Region number 1. Yeah, you can look at the board. You don't need to look at the notes. Region number 1, what does it look like? Region number 1, what does it look like?
That was the 1 in R.
Exactly, the one with the equation with R in it. And that's the incident ones. So region number 1, I think I erased that. Region number 1, essentially, let me write this down. Phi 1 just equals, first is 1 e to the positive kx, like this, and plus r e to the negative I kx. Exactly. So that's exactly what Aisha said. Yes, so this is the perfect. All right. And now I already showed you the wave function in the region number 2. That's the wave function in region number 2. Do you see that? So this is the region number 2. That's the wave function. Yeah. And then this is the region number 3. So region number 3 is similar to the region number 1, except that it will only have one coefficient in front of this. Okay, I think that's it. Yeah, region number 3. Can we use a boundary at x equals positive negative infinity?
No.
No, because what?
It's a traveling state.
Exact traveling state, you cannot use these infinite things at all. So this is that's a huge difference. I hope. All right, that's it. So we close this now. We do not need this. So I'm going to end this Zoom now. So okay, very good. So seems to be, at least from my perspective, you guys remember those things quite well. And today we're going to go over on this part. It won't take long for me to finish this particular part. The next thing that we are going to do is just match the boundary conditions. So I'm going to show you. So this is a region number 1. And so that's the wave function. So this is a region number 2 and region number 3. So region number 2 is here. So I'm going to box them such way I won't erase them. So this is region number 1, region number 2. And let me see whether my notation is good. Region number 2. Yes, I use A and B there. That's very good. And the last one, region number 3, did I use the... Yes, I did use the letter C. Yeah, so this is the wave function.
So, Dr. John.
Yes.
For region 1 and 3, I know that the coefficients are directly related because it's the intensity and the reflection. But for region 2, do the coefficients relate to those ideas also? Exactly.
A and B is going to relate it with a R. Yes, they do.
Okay.
In fact, in the end, you will notice that this C itself is also related with whatever before you will see that. And this relation is through the boundary condition, which I'm not going to. I will now start to explain this to you. So in other words, you're going to see me. We're going to repeatedly use three equations. And the last equation I used. Folks, to be more consistent with what our book used, and you will see me change this C. Everybody, change this to T, because it's a transmission one. There's no significance. Essentially, same thing. Just change it to T. And T means transmission, transmitted. When R means reflection, so it's easy to remember that. A and B, there is no such thing, so that's why I just leave as it is. And this is the equation which we will have. So that's exactly what we get. Now we're going to gradually solve for this one, and we're going to match the boundary condition exact the same way as we did last time. And there's no magic on this. Essentially, we just systematically started from the boundary condition. So this is the boundary condition match. So we're going to start with here. So last time we ended at 4. Now we're going to move on 5. 5, essentially, we're going to match the boundary conditions. So eventually you will get to see these equations comes out in exact same way. So here is number 5. We're going to matching the boundary condition for wave function. So for our wave function, we're going to match them in such a way we will be able to do that. So this is the one we are going to do. So this is looking, once we match boundary condition and then the wave function is done. So as this equation, so now we're going to go over first part A first. And this part A, I want to show you the boundary condition. So this boundary condition is at x equals 0, which is the boundary at this location. This is where the boundary is. So this is the boundary condition. So and then we will move on to the x equals A first. In this case, we have two wave functions must be equal to each other. So for the first is going to be a wave function in region number 1, which is over here, and then next we're region number 2. Let's do region number 1 first. Remember x equals 0. So this is my region number 1 wave function. When x equals 0, the first term is 1. And second term is plus r. So this is for my phi sub 1. And that I got. And phi sub 2 is going to be a, this e to the 0 of a, and next one a, b. So this is a plus b. So essentially, if I have these two wave functions matches each other, and then what I have is a 1 plus r equals a plus b. So that's it. So this is a plus b, like that. And the second is the derivative self equal to each other, so which means, so the derivative self equal to each other, like this. So the first order derivative is equal to each other. So let's go back to this equation. If you take the derivative for this equation, so you will end up with a ik e to the ikx, like this. When you take the derivative with respect to x, ik is coming down. And second term similar, but negative ikx is coming down like this. So the lower equation is a derivative of the top equation. So now we plug x equals 0 into here, and you're going to see another equation which is ik and a plus or minus ik r. So this is that when x equals 0, you have r minus ik. Here's ik, so that's what I have. And this is for the phi 1 prime. Phi 2 prime, if you take the derivative with respect to x, the q is going to come down. Q is going to come down. So here's a negative q is going to come down. And when you plug x equals 0, you're going to aq minus qa. So it essentially will be aq minus qb. And this is the one which you will be able to get it. So we can pull out this q out, and it's a minus b. Okay. So that's what we're going to solve. And you notice immediately, did you see, if I choose r as a real number, and a and b must be complex, because you have an imaginary in the front. That makes sense to you? Imaginary in the front. That's why this is going to come out. So I'm going to arrange this in such a way that I can look a little nicer. K minus r equals q a minus b. So that is what I have. And I'm going to both sides divide by q. both sides divided by q, so therefore I have this equation. So that's that. So this is the equation which we get. So this essentially maps the boundary condition at x equals 0. I will get this then. Now, so here's something very interesting come out immediately. You notice that if I give you the r, if I tell you the r, and then a and b all known now, because you see here, when this isn't known, so you can solve for a and b. So a and b so comes out immediately. You got it? Essentially, you can add these up. You get a 2a, 1 plus r plus I k, 1 minus r divided by q. So you see my a comes out immediately. So then this a is known now. So you have expression like this. That's good. So this is the one we have. And we do, when we minus each other, this the top equation minus bottom equation, I will have two b's. Minus of this one, two b's. So this will be 1 plus r minus negative this term. Here. So that's basically that. So you see I can find a and a b. All right. But this is not done with the quantization yet, because we still need to fix q and k. So that is our next job. Let me finish the next boundary condition. So this boundary x equals 0 case, and we have these relations. And in the end, we will get t here as well. I will leave my diagram here, and I won't erase them, so such way that you guys be able to follow the quantum well itself. And the barrier itself, this time we're going to move on to the next region, and this next part is going to come over this side. So in this case, what you're going to see is essentially the features which is quite important for our boundary. So this is the part B. We will have x equals a. Now, when x equals a, you should be very careful. Boundary is between the region 1 and 3 now. So this is 2 and 3. 2 and 3 now. So between these two. So wave function, you're going to see me to use the phi 2 equals phi 3. And these two is going to equal each other. Let's go back to what we get. So phi 2 is over here. So this will be x is becoming a now. So this you will see me right now. A little bit complicated, but not too bad. This should be positive. There's no imaginary. K. Oh, sorry, Q. Again, not Q. Q. And B term is a negative QA. So that's my B term. So this is my B term. So, and X all becomes A now. And now, for the region number 3, we have a letter T used. It's here T, and e to the I. T e to the I k. And this is the equation which we have. Are we good so far? Essentially, what we did was just plug it into x equals a, and then the derivative terms comes out in the same fashion. So the derivative of the phi 3 is going to be t I k e to the kx like that. This is the derivative. So I'm going to use the x to replace x by a. So you're going to see me write down a, that should be q e qa minus qa e to the negative qa. Yes, exactly. It's a negative qa. And the right-hand side is equal to the derivative. This is t I k e to the, so the t I k, not I, yeah, I k, and e to the I k, a like this. And you can, yes, go ahead.
Should the second term be negative QB?
Negative. Oh, forgive me. Yes, you are right. I made a mistake. Should be. Thank you. Correct my mistake. Yeah. This is what we get here. So now you can see we have this second equation. You probably noticed something very interesting going on here, which is the following. Did you see my A and B is a related with R? Did you see that? Did you see that? If I replace A and B into this equation, then you will see T is connected with the R. Did you see that? You know, if I plug in this equation to here, this equation here, and then the only term that you will have, you will see the R in this particular terms and T over that term. So that you will get it. You got it? So that is the main reason which we will have. Yeah. So this is essentially the key idea we will have directly. Now what we do next, we will let eta equals k over q. Let eta k over q. So the main reason we do that is because if you see, if both sides divided by k, and this k cancels out, so there's no more k's. By the left-hand side, so I'm going to simplify, this will be eta. I can pull out eta, by the way, and pull out eta. A e to the qa, b negative qa, and then over t I e to the I k a, like this. And this is the equation which we will have. And in the end, we can directly solve for this immediately. So now it's time for me to highlight what our goal, in the goal now. Let me call this equation number 1. This bottom equation, which is directly from this one, is called equation number 2. Okay, equation number 2. And I'll show you the key ideas immediately, because if I derive it, I do not. So the remaining part is all in the books, but I want to show you what actually our goal here will be. So, and now this equation has t. Once we replace that in by r, so this equation, this side will contain r. So this equation will contain r. Makes sense? So this contains r. So if I replace A with this equation, so it contains with R. There's no question about it. And this equation also contains R. Also contains R. Are we good? Are we good so far? Are we good so far? So this equation also contains R, like this. So in other words, if I replace A by R, B by R, and this will contain R. This also contains R. Now, the next thing becomes a little bit mathematical, but it's not that bad. So the final key idea is that this is the final step. There's no more dv then, and this will be final step. So I'm going to show you now. So the next step, what we do, we want to eliminate t completely. So what we do the following. 1 divided by 2. To eliminate t. So we essentially 1 divided by 2, you can notice that the right hand side both have t here. So this way allows us to eliminate the t. So this divided by that and eliminate the t. So therefore we to have an equation for R. And this is essence. And the remaining step, all mathematical tricks, which we will read the book together. Are we good in the sense that essentially what we did was we matched the boundary conditions, both the initial wave function and its derivative. Initial wave function and its derivative. Then we simplify such a way that this part is going to contain R, same thing down here. And that's end of the day. So then we solve for R. And this R will be a little bit complicated. For this reason, we're going to go to the book And I'm going to equation 2.6.10. So I'm going to write this down.
What page is that?
Just give me a second. I'm looking for it. Just give me a second. Okay, page 51. This equation 2, if you in your book will be equation 6 point. This on page 51. This is on page 51. So this is the equation which we are talking about. Do you find this equation? And this it's a very lengthy equation. I'm not going to write them down. So essentially what we did was that we solved 1 and 2. One case we solved for this guy, which is t times k t. The other is solved for x, because you only have 2 unknowns, right? You have 2 unknowns. One is r, one is t. R is unknown, t is unknown, so we just solve for them. And then you get equation for the e to the ik. The other is for the r. So that's exact equation which we got. Most of the book does not have this expression, which I don't like it, because students just really enjoy all the way to here, but they don't do anything. They always jump, so I plug it in that particular step. So this is when you solve for that. Now, did you see you get this hyperbolic sine, hyperbolic cosine? How do you get this one? Well, these will lead to the exercise homework. And you are going to figure this out, all right? It's not too complicated, but you do need some skills to work this out, but that's a practice purpose. So, questions?
I know it's for the homework, but is like the hyperbolic cosine, is that like something, do you derive that from mathematical wise, or is that something like a physics wise? You get something like that from?
Oh, you mean how do I get these?
Yeah, like when you get the hyperbolic cosine, do you derive that from a mathematical sense, or you derive it from like a physical sense?
Mathematical sense. Mathematical sense. Essentially, what I want to show you immediately was that if you have a coach like this, and what I did usually is do the following. You would notice some terms comes out immediately. Let me show you this as example here. Did you see I have e to the k, qa? Did you see the k? And this essentially just tells you, whenever you have this terms like this, it's going to have something like this. So in other words, whenever you see these 2 terms comes up, you assign them to coach like this. So that is all you need. And then when you derive at the point, you can see, okay, these 2 terms start to combine each other. They do combine each other, actually. So you will when you solve it, you will notice that they actually do combine each other. That's what you get. Okay. And I will give you guys plenty of hints. That's why I wait a few, maybe 1 or 2 more weeks. That's why we did not assign it. And I want to see where actually the hints the most useful for you guys, and then provide that hints for you. Essentially, I will break down those ones because this part is really, really nice, and show you. So essentially, what you're going to see is something like this. Okay. You just combine them together, and you get this expression. And it's not too long, by maybe 2 to 3 pages long. Not too long, not 10 pages, and that's what you're solving. All right. So, and then you notice that the r is a function of the q. R has a function of the q, and in that you see the r is a function of q. Similarly, for the t as well. So essentially, the r and the t are related with the q and k like this. So then you read the second sentence below equation 2.6.11. And you see by definition, diffraction coefficient r and the transmission t is related with the t r. So you see, now this comes out a t star like this, and r is going to be called lowercase r star, and that's what it comes out. And now the bottom equation, when you derive them, and then you basically calculate them, and in such a way there's no. So you have expression in the bottom of this page, on the same page. So this is what our page number 1. And then could you turn to page second page 52? Let's go to page 52, and there's the equation R plus T. R plus T. I've been able to see the R plus T, the equation. And the other equation is quite complicated, but if you read the sentence below, it says that these two numerator and denominator are actually exact the same thing. So that's why R plus T equals 1 in this case. So this is the reflection and transmission add up equals 1. This means results in particle conservation. So that's what happens. Okay, so, sounds good. This is the one that I found it's kind of enjoyable. And if you look at this equation, it's kind of complicated. So that's why I left out an exercise for you guys to prove they're actually the same. So this is the exercise 2.6.3, exercise 31. So that allows you to prove it. Okay. And that's the solution. So, and any questions before I show you some called physical meaning on this? Any questions? Okay. Let's have some physical meaning. And this part is going to be really, really important. And this is the, I'm going to write this down over here, physical meaning of this. Because we solve it, but we have something hide all the way. So we did not show you all the details. So this will be the last section. That's called section 5. 4. 5. Yeah, section 5. Physical meaning. Because at this point, you understand the solution is not that simple, but basically you could solve it without any difficulties here. But the key idea is that we want to know what actually this is about. So the first thing that we want to know is that how large K and Q are. So you see the entire calculation, there is no quantization equation. You remember, we don't have quantization. You never see anything of the quanta discretized. You did not see that. And these are determined, they are determined by our energy E. They're determined by energy E. So the tunneling the features is non-trivial. It's determined by tunneling E. Why determined by tunneling E? And you remember, did you see here, for instance, did you see I have a K squared here? Did you see a K squared? Did you see I have a Q squared here? Did you see a Q squared here? In other words, tunnel is different. You have to tell me how large this E is. If you did not tell me how large this E is, I stuck how large your Q would be. If the Q, you don't know the Q, forget me, none of these will be known, right? None of these will. So in other words, the tunneling, you have to tell me E, how large this E has to be. Because there's no quantization you determine. That's a huge difference. So essentially, that's what I said here. It's determined by this E. So 1 E gave you 1 K and 1 Q, like this. 1 E gave you 1 K and Q, like this. So you have to tell me how large this E that would be. And then when you have 1 KQ, it gave you 1 R or 1 T, like this. So essentially, this tells you the key features on that. And for this, we're going to show you the diagram. And this is, I purposely designed. Could you guys go to page 53? Aisha, this is the figure 2.10. 2.10. Figure 2.10. This is, I numerically solved everything of this. Folks, it's not simple in the sense that, you should be, some books, they do not have these figures at all. And I want to show you what each of these figures is all about. Figure A is our incident wave, which means, you remember, we talked about this wave is propagating from here. Did you see this is the incident wave which we have? All right, that's incident wave. And B is a reflected waves. You know, when it's a reflected, it's a reflected like this shape. Now, A and B, these waves, I have an amplitude 1, essentially amplitude 1. So this is how much the wave is going to, but it's not perfect 1. If you look at the B, you see the B is less than 1. Did you see that? Did you see less than 1? Are you being able to see? The amplitude for the B is smaller, a little smaller than A. This is because some of this wave is transmitted, but the reflected wave must be smaller, otherwise you could not add up to 1. You won't be able to. So that's why this is a reflected wave. The part C is a barrier. In other words, inside a barrier, this inside a barrier, how the wave look like. So the real part is you get a decay function, and this part is increased this way. And you notice also the amplitude there is larger. When I first time looked at it, oh, my calculation must be wrong. How the wave function larger than 2? You normalize the gate 1. Well, if you did not normalize it, your wave function could be larger than 2. It doesn't matter. Because your region is small. You remember, your region is small. If regions are large, sorry, you cannot do the integration, give you entire results 1. I'm not sure whether you understand what I'm saying here. In other words, you can have one region wave function very big. The other region will be smaller. But the region that is very big ones, you cannot extend too long, because otherwise when you do the interval, you get larger than 1. That's not possible. So this is the main reason. Okay, so this is. And the D is a transmitted ones, which means it's just transmitted through the place, which is region number 3. So these are all separate. When some of my colleagues said, originally I did not separate them, so the student could not see them clearly. So this time I separate them completely. So you know it's separate region. And let's look at the E. E is a total wave. Total wave, now you can see the incident part is from negative 50 angstrom all the way to 0. So my region is about 5 angstroms thick. So the barrier, so from here, this A I choose 5 angstroms here, from here to 5 angstrom. So, and then this is 50 all the way to that. And then from here is another 50 all the way to that. So that is what I have. You see, in the region of barriers like this small, but when you transmit it, and that's how small the wave becomes. So this, the red, the black curve is the real, and the red curve is the imaginary part of the wave function. Originally, I just simply used, like other books use, just like density. Student doesn't like it, because if the density, everything is meshy like this. You have so many beating on this. You did not see the wave. Here's the wave which we got. Are we good? Are we good? So that's, yes, go ahead.
So for when you look at the angstrom graph, in the negative region, it's kind of like they're opposite each other, the real and imaginary.
Yes.
But then once you go into the positives, they kind of like they kind of are not opposite of each other. They kind of shift.
Yes.
So why is that?
The real, let's look at just the A first. Let's look at A. This is actually plotting this way. I'm glad you asked me this question. I'm not going to erase any of this, and I'm going to write this down. So, essentially the incident wave coding we plot this way. So the shifting is due to one case we use the cosine function, the other use the sine function. So when it is the sine function, when the cosine function. The cosine function, they is spatially shifted because you remember the sine function look like this. That's a sine. The cosine function look like this. So there is a spatial shifting. That's the 90 degrees shifting. That is where you see the shifting. So everywhere you have see the real and imaginary part are always shifting like this. You do not have exactly the same. You do not have. Okay, so this is the one that I want to show you first. Second, which is most exciting, go to page 54 and figure 2.11. Page 54. This one is my comprehensive wave, and I'm very proud of how to show you this. In this case, the first A graph, our barrier thickness is 10 angstrom, And V0, which is the barrier height, that's the barrier height. Remember, V0 is barrier height, is 1 electron volt. And my E, did you see my E there? E equals 0.2 V0, which is 0.2 EVs. That's where the incident energy enters. In other words, that's what I said. Okay, you have to always tell me how large your E is. Otherwise, I cannot do the job. So that's where the E comes out. So now the first one you see, if I use this, you see the transmitted wave is almost to zero. Did you see? Almost to zero. Transmitted is almost no transmit. Everything is reflected this way. Now if you make the barrier smaller, which is B, barrier in this case is the 5 angstrom, not 10 angstrom. And then you see the barrier becomes small. So now you see the wave propagates quite strongly. It comes out more visible in that case. Did you see it a little more in comparison with A? Figure C is the most exciting one, I would say. So I now increase the energy to 0.5 electron volts. So in other words, incident energy becomes larger. Now if you compare the A and the C, you notice the C is a transmitted one is almost to zero. But now, if you have more energy into that, you will see some clearly visible difference. So you see, if I shoot electrons into with very high energy, they get transmission into the barrier, whole lot more energy goes with how large probability goes there. That's the difference. Now, I just want to show you systematically what is happening. Did you see I plotted D? That's transmission coefficient as a function of energy. So if my barrier equals 1 angstrom, which is really tiny angstrom, you see the transmission gradually increases like a power law, essentially, then gradually saturates. It never exceeded by the 1. It's always saturated to 1 because that's the maximum possibility. Now, did you see I stopped at 2? The reason was that I'm using the barrier. I think in that graph is used the 1, something like that. Yeah, or maybe 2, like that. I forgot to write this down. Anyway, so that's that. Now, just to prove that our transmission law is correct, did you see E? I calculate R plus T. That's a solid curve, the black solid curve with R plus T. So this must be 100% equals 1. That's actually you asked me before. T plus R must be equals to 1. That's why it's always this case. So I even plot them and all the after decimal point, everything is 0, 1, all 0. So which is really beautiful. And one last thing is how the transmission as a function of the thickness of the barrier. So this is how thickness of the barrier. You see, if you are within the 2 angstroms, the transmission coefficient is large. But once you over 2, it drops very precipitously. And this is the example number 12. This shows you that particular features. And so I am not going to run over the time, so this almost time ends now. That's the last class of this chapter. This is the last chapter. And I hope you guys enjoy enough. And next week we're going to talk about harmonic oscillators and operators. It's a little more slightly different nuance. Okay, sounds good? Any questions? Yes?
So does that mean that the A, the thickness, does that relate to R?
Yes. If you have this, you talk about this little A, right?
Yeah.
Yeah. Essentially, when the A becomes smaller, R will be less because you have less refraction. Lowercase r is going to less reflection, be more or less like transmitted.
And that's why it comes out.
Yes, that's why it comes out. Yes. The thinner comes out more, obviously. Thicker comes out less. And that's why in the beginning, I think either Cody or Tobin asked me, how do you use this in the regular circuits? That's qubits going on. That's the thickness of aluminum. Yes, I did wrote it somewhere. Aluminum, yes, here you can see. That's why thickness of aluminum oxide must be thick, must be not thin. So therefore, these two will be able to go through the tunneling barrier. Otherwise, it won't be able to work. So that's the key. All right, that's it. You got a question about the homework and which part you are interested in, which step you want me to go through it. Could you show me, let me turn off the camera. I don't need the camera at all. If you're good, just turn that in.